Thank you. And I'd like to thank the organizers for the invitation to speak here. It's been a very educational week. Lots of very nice talks and nice people to talk to. So thanks to the organizers and the staff for making this possible. So I'm going to talk about some works on phase transitions in the frog model. This is joined with my colleague Jonathan Hermon and our students Daniel de la Riva and Yuliang Shi. So this picture, by the way, since people were commenting, so I gave a talk about some related work a year and a half ago or so near Munich. And as I was preparing my slides, it was at this institute at the outskirts of Munich, and I go there and I go to the library. And in the library, there was this statue of the frog. So I thought it's very auspicious and took a picture for my slides. So, not everyone is usually familiar with the frog model. So I'll start with a quick overview of what it is and where it comes from. And this is a special model, a special case of a class of models that are referred to as the A plus B models, which you can think of them as modeling the spread of a rumor or infection in a population. So you have a population moving around in some space and interacting. Some of them are infected, and when two particles meet, if one is infected, the other becomes infected. So it's a very simple and natural model. The specific model, so we have some graph. There's a pointer here, I think. Yeah. Is this a pointer? No, it's not a pointer. That's a pointer, maybe. Yes. Yeah, so anyway, we have some graph which can be anything, and it will be various things later. And on the graph, we have particles. There are two types of particles, A and B. And you can think of B as being the infected particles, and the particles A are the uninfected ones. And they move around. So in the general model, people consider cases where they move around with diffusion rates dA and dB for the two types of particles, which can be anything. And as we said, if there are particles of both types at the same site, then they instantaneously switch to type B. Now, there are several variations on this. Some of them are that the particles of type B can revert to type A. So if you're infected, you can heal. If you know the rumor, you might forget it. So maybe there's some rate of doing this. The frog model has a different variation where the particles have a finite lifetime. So once a particle has type B, it moves around for a while and then dies. But there are several variations on this that people are interested in. And OK, so there are many initial conditions you can study. The most commonly studied one when you have a Poisson process of particles of type A, and then you introduce a particle of type B, and you ask how this affects others. And of course, it's possible if particles of type B can change back to type A or die, then it's possible that nothing happens. The particle of type B dies, and the process, we have only type A after a while. Or it's possible that the type B particles survive. So so there is some possible transition here, depending on the different parameters of the model. We have the movement rates. We have the rate at which particles change their state spontaneously. And if the process does survive, if the type B particles do live forever, you can ask where are they located. So is the number of such particles grows predictably? Is there a limit shape similar to the first and last passage percolation, where you expect them to feel some limit shape which grows linearly, maybe up to time t? So there are various results along these lines. Some of the earliest are from Kesten and Sidorovicius and Liorola, and many other people have worked on this over the years. But I'm going to start specializing towards the frog model. So So the frog model is a special case of this. So the particles of type A are sleeping frogs. So we start with the Poisson process of sleeping frogs shown here on this field. So most of them are asleep. And so the sleeping frogs don't move at all. So the jump rate from them is 0. And then we have the active frogs, which have jump rate 1. So you can do this in continuous time or discrete time. So nothing that I'm going to say today is too dependent on whether it's discrete or continuous. I'll talk about continuous time, but everything translates if you really prefer discrete time. So the active frogs perform a random walk, just a simple random walk on the graph. Now the active frogs has a lifetime which is called L here, but later we will call it T. So when the frog is active, so it jumps around for time t, and then it dies. So it stops, so it doesn't fall asleep, so it just dies and it no longer plays any role in the system. And okay, and the main questions that we are interested in, so does the process survive? Are there active frogs at all times? Each individual frog, of course, will only live for a finite time, but if they do survive, what is the limit shape for the set of locations of active frogs? If there is a limit, what you say about the growth rate? For finite graphs, people were interested in how long it takes this process to cover the graph. And there are many other questions that people have studied in the past. And a brief history of this. This was introduced by Alves, Mercado, and Popov. And they discussed it on ZD, and they said, okay, there is a phase transition. So so there are two parameters here, the lifetime of the frog and the intensity of frogs, the number of frogs that you start with. So we consider the case where you start with the Poisson number of frogs at each vertex. So you have some parameter lambda for the average density of sleeping frogs initially. So they said there is a phase transition if you have sufficiently many frogs initially, then the process does survive on ZD. And there's been a long list of papers extending and studying other properties of this. I will not go over the whole history. But rather I want to tell you about, to get towards our work. And there are two things two main results that I'm going to talk about. So the first is existence of the phase transition. So it's not completely obvious that this model has a phase transition. If you have, depending on lambda and t, maybe the process dies for any lambda, and maybe not. So one question is the existence of the phase transition. The other question is about sharpness of the phase transition. So for reference, this is a little bit about sharpness of the phase transition for classical Bernoulli percolation, which I assume you're all familiar at least with the model, if not with the results. And for Bernoulli percolation, you just have edges or vertices of the graph are either open or closed independently. There is a critical density P above which we have an infinite cluster with positive probability. This is for say, a transitive graph. And the sharpness of the phase transition says, so there are various formulations of this, but one of the formulations is the follows. So if P is larger than PC, then not only is there a positive probability of having an infinite cluster, but there is actually a bound on the probability of having an infinite, that the origin is in the infinite cluster, or the density of the infinite cluster, which is linear in how far you are from PC. So it's some constant times P minus PC. That's the low bound. And on the other side of the phase transition, if you are below criticality, then the probability that you have a large cluster of size at least n, not only does it decay to 0, but it decays exponentially. So this is one of the standard results that would be referred to as sharpness of the phase transition. So below PC, the clusters are not only finite, but really small. Above PC, they are not only do we have infinite clusters, but we have a lot of them. And this has been, there have been various proofs of this over the years, going back to works of Menshikov and then Eisenman-Barsky, and then the most recent proof by Domenico Panentacion, which is also was inspired for some of our arguments, inspired some of our arguments, is the following idea. So, so they say for percolation on a transitive graph, they say that they give a criterion for P being subcritical. And the criterion is as follows. So for a given set S, so you look at the finite set S that includes the origin, the red dot here, and we ask how many points X are there on the boundary of the set so that the origin is connected to the point internally to the set. And we call this phi of S. It's the expected number of ways, if you start at the origin, the expected number of places where you can exit exit the set without leaving the set previously. And the criterion they have is that P is less than PC, the process is subcritical if and only if there is some set S where this number is less than 1. And in fact, you can show if this number is less than 1 for some set, then you can make it arbitrarily small. There will be sets where it's arbitrarily small. Whereas if you have a positive probability to have an infinite cluster, if you are above PC, then you have at least one way to exit if you're in the critical cluster. So this probability is bounded below by some constant for all S, and in fact, it will be large for large sets S. And okay, so well, maybe yeah. So this is sort of this picture here is sort of a rough idea of how this is used to prove the sharpness of the at least part of it to prove the exponential decay. And the idea is that if you have such a set S, suppose we found some set S where phi is less than 1. So we have this initial root here, and we have the set S around it. And on average, we have less than 1 points where we can exit the set. But maybe in this case, there are 2. So then we can draw another copy of the set. The graph is transitive, so we can draw a copy of the set around this point and a copy around that point there. And for each of those copies of the set, we can ask how many ways we have of exiting those sets. And in fact, you can restrict yourself to ways that avoid the previous parts of the cluster that you've already seen. So this gives you some negative information. So there's going to be on average even less. And you can keep going. Each time you manage to exit the current set, then you look at another copy of the set, and eventually what you end up with is saying that you have some structure that is somehow representative of the cluster of the origin. And this cluster is dominated by a subcritical branching process. And so, the subcritical branching process, you have exponential decay on the Stas probability that it's large. This gives you the exponential bound. I'll say a bit also about the upper bound later when we talk also about this in the context of the frog model. So that was a bit about the classical Bernoulli percolation. And so these are the main results that I want to discuss. So first of all, if you have a transitive graph which has a superlinear growth, then we have a phase transition in T. So again, we have a transitive graph. The growth rate, you say, what is the size of the volume? So superlinear, it grows faster than linearly. So it's not just a copy of Z, for example. It's not virtually Z. Then if T is large enough, then lambda C of T is finite. So if you have sufficiently many frogs at any site initially, then the process survives with positive probability. And by the way, if anything is unclear, feel free to jump in with questions or corrections. So, but on any transitive graph of superlinear growth, there is a phase transition in t, so in lambda. So as long as the lifetime t of each frog is positive, so t should be strictly positive, and you have sufficiently many frogs initially at any site on average, then with positive probability the process survives. And
sorry, I mean, there's one. Can I ask you a question?
Yes.
I'm a little confused. I mean, the frogs die, right? But the new frogs coming. So
yes. So we have an initial percolation, initial configuration of frogs on average lambda at each vertex, and we introduce one active frog at the origin. Now the active frog is going to die out, but before dying out, it possibly wakes up several other frogs.
They also die.
And they also will die, but that's right. So each individual frog will die out eventually, but it's possible that the whole process die out, that at some finite time there are no active frogs.
Oh, I see, because you have an infinite graph, you have...
Yes. Yeah, crucially, this is on an infinite graph. On a finite graph, of course, after a finite time, you either exhaust everything or everything is sleeping still. Yeah, so this is only on infinite graphs. Infinite, connected. We talk about transitive. You can do quasi-transitive without much work. More general graphs, all sorts of things could happen. So, okay, so for the phase, so again, we have two parameters here, and let me just note this here. So we can consider p lambda t. So this is the probability space on a given graph. The graph is implicit, where you have intensity lambda for frogs initially. So we have Poisson lambda at each vertex, and t is the lifetime of the frogs. And so we are asking for which lambda and t is the probability of survival. So the event of survival is that at all times there are active frogs. And this is equivalent to saying, let me just note this here. So for all time, there exists active frogs. And this is also equal to the statement that infinitely many frogs are activated. So of course, you can imagine a configuration, you can imagine some scenario where infinitely many frogs are activated before time 10 and then they all die. But that's not going to happen. That's easy to show. So if the process survives, then there will be infinitely many frogs activated and vice versa. And so the second theorem is slightly less general. So for a phase transition in T, okay, the phase transition for a fixed T, when you make lambda grow, this is for any transitive superlinear growth. For the second theorem, that there is a phase transition in T for a fixed lambda T large enough, the process survives. Then for this, we do this on non-amenable graphs, and we can do this on graphs with polynomial growth, where the volume of the growth of the balls grows polynomially of degree more than 1. We do not have an argument for completely general graphs, but okay, this covers most interesting graphs, but certainly not all. And so we have a phase diagram that is sort of crudely pictured here. So you have lambda, you have t, and there is some critical curve, so that below the critical curve, I should annotate this. So here the process dies, and here you survive. So if lambda is large enough as a function of t, if t is large enough as a function of lambda, then you have a survival. Whereas if below the curve, the process dies out. Now, I should comment the existence of the subcritical phase is much easier to see. So that's the easy part is that if p times t is less than 1, then p lambda t of survival is 0. So if you have this hyperbola pt equals 1, then below this hyperbola, the process dies out. The reason for this, each frog does a random walk at rate 1. So it activates on average, it reaches t new sites. At each new site, it reaches on average lambda new lambda frogs. So the average number of frogs that an active frog is going to encounter is lambda times t. If this is less than 1, okay, it's very believable that this makes it die out. In order to make this precise, we rely on something called the abelian property of this model, which is also going to be useful for other parts of the argument. So what is the abelian property of the argument? So of the model, and this holds for a number of other models. The idea, including various sandpiles, for example. So the idea is that the order in which you explore the sequence of events does not affect what's going to happen. So you can imagine that every frog has some trajectory that it's going to follow if it's ever awakened. So it has some trajectory that's written on a piece of paper in its pocket. And if it wakes up, then it's going to take this piece of paper, start following the trajectory until it dies. So instead of letting the frogs move simultaneously in real time, you can also do this in another order. You can say, okay, we activate this frog, let it move maybe all of its trajectory, maybe part of its trajectory, and we note which frogs are activated. And then you can pick each time one of the activated frogs. And you can select in a completely arbitrary way which frog you look at next, and let that frog move either part or all of its remaining trajectory, and keep going. As long as there are some frogs that where you have not yet seen the entire trajectory, then you pick one and keep going. And as long as every frog that is awakened eventually gets to do its thing, then the set of activated frogs will be exactly the same. The order doesn't matter. The time at which a frog is activated will change, and the sequence, so if I have a frog here, so maybe frog A we start here with frog A, which activates B, which activates C, which activates D, which activates this frog. If you do this in a different order, then the chain of activations could be different. But whether some frog Z here is going to be activated or not does not depend on the order of activations. And so that's the abelian property. And in particular, the event that infinitely many frogs are reached, you can just determine this. For each frog, you can ask, is there some chain of activations that lead to that frog? And this determines whether it's going to be activated or not. Now, if lambda t is less than 1, sorry, there's a p there which should have been a lambda. And so if lambda t is less than 1, okay, so the first frog activates on average lambda t frogs. When you look now at the second frog, so some vertices have already been visited. So if the new frog reaches a vertex that's already been visited, there's nothing there, and there are no sleeping frogs there. So and the number of new vertices that it reaches is still at most t on average. So that's why we are dominated by a subcritical process. So we have this hyperbola, and below which the process easily dies out. And the main challenge is to prove the existence of a phase of the surviving phase, of the supercritical phase. So this is about the phase transitions. And I'll just say what are the results about the sharpness. So for the sharpness, we have the subcritical and the supercritical phase. So if lambda t is below the critical curve, then we have exponential decay in the size of the cluster. So the size of the cluster is, you can think of it as the number of activated frogs or the number of vertices that are reached. So we have exponential decay for those, for the tail. And above the critical line, so the probability that the process survives, the probability if you start with a single frog that you activate infinitely many frogs, it grows linearly in the distance from the critical curve. Any questions at this point?
The critical curve is exactly lambda t equal 1?
It is not.
Okay.
You can easily push a little bit beyond.
But you have a formula or you don't know it?
No. So you can easily push a little bit beyond lambda t. So this argument is somewhat wasteful. You do visit, so each frog has some chance of visiting previously visited vertices. So you do wake up on average less than lambda t. So it's easy to push a little bit beyond lambda t equals 1. You can get lambda t less than some function of the graph. We don't know exactly what is the critical curve. You should think of it as asking, okay, what is the critical parameter for percolation, which also is almost never known. So it's only known in some very special cases where we have miracles. Well, we have the next talk about miracles. So, but generally we don't know what is the critical curve. Yes.
Do you think there's like a universal constant, say that lambda t is bigger than c, then it's supercritical? So it's basically like between
Yes.
two hyperbolons.
Yeah, I would think that. Well, for quasi-transitive graphs, maybe not. For transitive graphs, if I had to guess, I would say yes. But and certainly, it is possible to get some asymptotics for this curve, both both in this direction and in that direction. And in the asymptotics, these things are fine. So asymptotically, this curve does look like a hyperbola on both ends. Okay, so we get to the most important slide. This is generally good advice, but we're going to get into some details here, which are maybe not as nice. So if you don't like them, remember the slide. But we'll turn off now the slides and switch to the board for some proofs. Okay, so let me tell you some of the ideas that go into the proofs of this. So the easiest of the three theorems is that if lambda is large enough, then the process will survive. So if you take t fixed, lambda sufficiently large, what's the argument here? We can just compare it to Bernoulli percolation. So how do you do this? You just say every time you reach a vertex, you wake up lambda frogs, a million frogs. So if t is very small, then most of these frogs will actually just die and not go anywhere. But if lambda is sufficiently large, then many of those frogs will jump. And you are very likely that you'll have a frog jumping along each of the edges. So then you can just declare an edge open if you have a frog at one endpoint that moves to the other endpoint. And you see that if you have such an infinite cluster of open edges, then you also activate infinitely many frogs. And so you just compare to Bernoulli percolation. So you just argue that the process dominates Bernoulli percolation. Bernoulli percolation is known. It's known that if you have a transitive graph which has a superlinear growth, then PC is less than 1. This sounds simple. This is not an easy result. This was proved only a few years ago by Duminil Kopan and several others. Let's see. So Goswami, Severo, Yadin, Raufi. So that's not an easy result, but it is known. So the case when t is fixed, we can just do this. If lambda is fixed, t large. So this requires some different ideas, and there's two different arguments. We said one in the non-amenable case, one in the case of polynomial growth. So let's consider first the case when G is non-amenable. Well, if G is non-amenable, so if you have some finite set S, or let's call it A, so for every vertex in A, you can ask what is the escape probability, the probability that the random walk from X exits the set and never returns. So this is the escape probability, let's call it EA of X. So this is the probability starting at X that the heating time is infinity, the return time to A is infinite. So there's the general fact that if the graph G is non-amenable, then the sum over all A of EA of X is at least some constant size of A. For a non-amenable graph, the sum of the escape probabilities is linear in the volume of the finite set. And the consequence of this is that some constant fraction of some delta fraction of the points have an escape probability which is some delta. For some delta depending only on the graph, not on the set. So we have many points from which the random walk is unlikely to return. Of course, we don't care about never returning. We only care about not returning up to time t, which is also enough for us. And another effect for non-amenable graphs, if you perform a random walk up to time t, then the trace is going to be linear with high probability. So you visit a linear number of vertices up to time t with high probability. So from this, we can deduce that there are many vertex X in A, such that a frog from X is likely to visit many vertices Y which are not in A. So many is, let's say, T over 100. And likely is at least probability at least 1%. All the numbers depend on the graph. So how do we use this? What we say, we start with a single frog, and it has some trajectory, which is likely to be large. We want to eventually get some supercritical growing process. And it's not uniformly supercritical, since if you have some frog that is somewhere inside here, it's probably going to spend most of its life, maybe all of its life inside the set that's already been activated and doesn't give us anything new. But here we use the abelian property. We can choose each time which frog we want to look at next. And so we are going to pick some frog that is in one of those good vertices that are near the boundary where the random walk is likely to exit. And so we pick such a frog. It has some trajectory. Maybe the trajectory is small, but there's a good chance the trajectory is large, and then we just add the trajectory to A. So the set A of activated vertices grows, and on average it grows by something more than by something large. So again, if T is very large, even if T is very large, even if the average number of frogs is very small, so each time we get a frog, it's going to give us a large number of new activated vertices. So there is a good chance that many of them will have frogs. So if T is 100, so if the number of vertices we reach is 100 lambda, then on average we have 100 extra frogs here. And so now the idea is that we look at this set A. We have some subset of A which are the set where we already looked at the trajectories of the frogs. So each time we explore the trajectory of a single frog, so the set of revealed trajectories grows by 1 each time. The set of activated vertices grows on average by more than 1, because each time we pick a vertex near the boundary where we are likely to grow more. So you have these two sets, the revealed frogs and the activated ones. And the activated ones grow on average faster. And from this, it's a standard martingale argument to show that with positive probability, it stays strictly above the revealed ones, so that you always have more frogs to reveal. So this is the rough idea of the non-amenable case. The polynomial growth case is more delicate. The polynomial growth case relies on the structure theory for transitive polynomial graphs. This goes back to the theorems of Gromov on polynomial growth groups and the structure theory that was used for many other things, in particular for the locality of the percolation probability for polynomial growth graphs. So this was by Contreras, Martineau, and Tassillon. So I will not say what they did, but the polynomial growth. So the fundamental idea is to find a substructure inside the polynomial, the graph, where we will eventually get percolation on this substructure. So what they do is we can find some, so these are balls of radius r. So r is going to be very large. We fixed some intensity lambda of frogs, and r will be large enough in terms of that. And so those are balls of radius r. They are disjoint. And you can consider this meta graph where two balls are adjacent if the distance between them is at most some constant times r. So this is this meta graph where let's call it G hat. So these are, each ball corresponds to a node, and they are connected if the distance is at most, say, 5 times r. And what is known, this is a part of the structure theory for polynomial growth transitive graphs, that we can find such a net, so there exists some r and some g hat, so you can select these balls such that PC of G hat is less than, let's say, half, or you can put any number you want here. So the critical parameter for this meta graph, you can make it less than 1. So that's one ingredient. Now, what we want to show, if you start a frog in here, we want to argue that it's going to, we want to eventually get some percolation on the meta graph. So so how do we go about doing this? First of all, we want to argue that the frog inside here is reasonably likely to activate either all or most of the ball that it lives in. A single active frog here is reasonably likely to do that. And the idea for that is that if the lifetime is large, and we take a sufficiently large lifetime, and then the radius is such that most of the life of the frog is spent inside the ball. So if t is sufficiently large, so for t large, r larger than, let's just say t squared. So the time to exit the ball in this essentially polynomial growth is on the order of t squared. The two-dimensional cases may be a bit different, but let's not get into details. So for this, a frog is likely to encounter many new frogs, many new vertices inside the ball. So we have such a ball B. So a frog typically visits many sites in the ball. A frog, if it starts anywhere in the ball, then it visits many new sites. But we can say more than that. So if you have a set A inside the ball B, and the size of A is less than, let's say, B over 10, then you get many new sites in B minus A. So not only, so if you have some subset of A here that has already been explored, then a frog anywhere in the ball is reasonably likely to visit many new sites. And this does rely a bit on the graph. So you can imagine that if you have a set A that is something like this, so if you start a frog somewhere in the middle of this, so it's going to take it a while before it can reach any new things. But T is going to be roughly the time that it takes to exit the ball. So we use some heat kernel estimates for random walks on such transitive graphs of polynomial growth to deduce that the frog is reasonably likely to visit also the sites that have not yet been explored. And so, okay, so if you have a frog in here, then it's likely to find many new frogs. And those frogs are likely to, again, find many new frogs. And you can keep going until you've explored some constant fraction of the ball. Now, if at some point, so you have a super critical process, if it dies out, you just can start another frog, and maybe this frog will activate a lot of the vertices. And the final result of this argument is that with high probability, there are many frogs in the ball, so that if you activate that frog, it will reach a large fraction of this ball. And then, okay, we can use Poisson splitting and the abelian property, just do all of this with just half of the frogs. And then the other half of the frogs you have not looked at yet. And those frogs are going to have their own independent trajectories. And once you reach some constant fraction of the ball, you will reach all of the ball. And also, once you've reached those frogs are also likely to reach many vertices in the adjacent balls. So once you do this, the conclusion is that there are many vertices in each ball with high probability. There are many vertices, so that if you activate that vertex, then it will reach all of the ball and also adjacent balls. And at that point, you compare it to percolation on this meta graph. So you activate all of this ball, which activates all of the adjacent balls, which activates all of this. At some places, this fails, but this is where we use that PC for the meta graph is small. So this is how. So this is the outline of the proof in the polynomial growth case. Now, given the time, I'm not sure if I should say things about the arguments for the sharpness or stop. So who's in charge? You're in charge. Do I have time or? Don't remember. I think we started slightly late, but I don't remember exactly.
Maybe a couple of more minutes.
A couple of minutes. Okay, so well, okay. So as I said, the proof for the sharpness of the phase transition is inspired by the proof for percolation of Dumilin-Kopanen-Tassillon with this finite set. So fundamentally, there's a similar idea. We find a local condition that gives subcriticality. So you have some set S, and you look at you have some frog inside here that maybe activates, has this trajectory, and then we have a frog here that has this trajectory, and a frog here that has this trajectory, and maybe this frog exits. So this sort of sequence of activations gives us a contribution to some quantity that we count. We want this to be small for the process to be subcritical. For various technical reasons, actually, we need that all of the intermediate frogs not stay inside the set S until they die. So if this frog were to go out here, then that's not good for us, even though the sequence of activations happen inside S. So we have this modified version of phi, and again, you can argue if this is small enough, then the process is dominated by a subcritical tree. If this is uniformly large, then we use differential inequalities, which is also what was done in the in the Bernoulli percolation to show that the probability of survival goes linearly in the distance from the critical curve. So there are various technical difficulties that are new to this model because of the dependence. So when a frog goes somewhere, it will actually continue. So it will not just reach here, it will reach several things outside. So this leads to all sorts of complications. So it's not directly applying the previous argument, but okay. But at the 2-minute outline is this. So if people want to hear more details, we can discuss in the break. Okay, so thank you.